So I would like to thank the organizer and Françoise Dalbeau for inviting me to talk here. It's a pleasure. So, is the recording okay? Yeah. Okay, so my talk is about precise statistical properties of the geodesic flow on periodic hyperbolic manifolds. So I have two disclaimers to make. The first is that the geodesic flow on periodic hyperbolic manifolds is only one of many motivations for my work. The second disclaimer is that my work is essentially a work of probability and analysis. So I will start with geometric examples, but I will try to get rid of the geometry as fast as possible. So first I will recall some properties of the geodesic flow on hyperbolic manifolds. So if we take manifold M, which is compact, connected, and with negative sectional curvature. I will study the geodesic flow G bar T on the unit tangent bundle. And there is one very natural measure, which is the Liouville measure, which I will denote this way. This is a Liouville measure. And I will assume that it's a probability measure. So the picture we have in the classic example of hyperbolic manifold, this way. So, in this context, this flow will be ergodic. So by Birkhoff theorem, if I take any integrable function on the unit tangent bundle, the limit of the Birkhoff integrals, correctly renormalized by 1 over t, will be equal to the spatial average of the function f. Well, but if f has a zero integral, all it tells you is that the Birkhoff integral grows as speed less than t. So this is not the correct renormalization. I mean, it tells you that it converges to 0, but you can do better. So another second theorem, which is the central limit theorem. If I take a function on the unit tangent bundle which is older and has zero integral, then the correct renormalization is not 1 over t, but 1 over square root of t. And the limit object will be a bit different. It will be some constant which depends on f times a Gaussian, and the convergence is in distribution when this function are seen as random variable on the unit tangent bundle with the Liouville measure. And the constant C of f, actually C of f, it will be a semi-norm, which is induced by semi-definite inner product. And it is equal, it is positive, and it is 0 if and only if f is a coboundary. Because if f is a coboundary, you can, well, this will be bounded. So this is just a central limit theorem, which you can, yeah. There is a measurable function which, well, with flows it's a bit harder to define, but you can see that a coboundary, it will be this. There exists a measurable function with this property for all t and everywhere. Well, this central limit theorem can be slightly improved. I said that it's converged in distribution as a random variable seen on the unit tangent bundle with the Liouville measure. Well, I can replace it with any measure mu, such that mu is a probability measure on the unit tangent bundle, and mu is absolutely continuous with respect to the Liouville measure. So that is a small improvement on the central limit theorem. The idea is that the limit distribution is a local property of the system. I mean, you can't share the manifold into two parts, so that the limit on one part everything will be positive, and on the other part everything will be negative. The limit distribution will be very much local. So that's the results for compact manifolds. But my work is not on compact manifold, but on periodic manifolds. With perhaps. So my second part will be on periodic manifolds. So I take an integer d dimension, which will be 1 or 2. And I will choose a manifold n, which is ZD cover of M, connected ZD cover. So the idea, well, I have a geodesic flow GT on N, on the unit tangent bundle of N. And Liouville measure which is a measure on the unit tangent bundle of n. But n is not compact anymore, and the Liouville measure will be an infinite measure. The ZD cover, it means that we have an action of ZD on the fibers, which is free, transitive, and behaves well with respect to the projection onto him. So to see exactly what such a manifold looks like, well, I will start from the manifold I've drawn here. And I will cut some handles. So I will do a cut here, for instance, and a cut here. This gives me a manifold with boundary. And I will take many copies, ZD copies, of this manifold. So for instance, for Z equal 1, I will have one manifold. Another manifold. Etc. And I will do some cutting. Now I will do some pasting. So for instance, this one and this one goes together. I will pass them together. I do this on each copies. And I want everything to be connected. So for instance, this one and this one goes to go together. So that means that this one and this one go together. So for instance, I will pass this one with this one. I will pass this one with the following copy. And this one I will pass with some copy here. What I get is a connected manifold, which will look like this. With infinitely many holes. You can do the same with in dimension 2, and then you get some kind of array of well, your manifold will look like a bit like a will look a bit like a plane. And then I want to study the manifold on the geodesic flow on this manifold. And the good heuristic to have is that the geodesic flow on such a manifold behave a lot like a random walk on ZD. So I have two theorems which are a bit equivalent to the theorem here and here. So I will assume that D equal 1. So for all integrable function, the fact is the geodesic flow here is still ergodic, but the ergodic measure is infinite. So the Birkhoff theorem does not work anymore, and the limit theorem will look a bit more complicated. So for all integrable function, no, there exists a constant C such that for any integrable function, the limit of 1 over square root of t of the Birkhoff integral is equal to the constant times the integral of f times the absolute value of Gaussian random variable. So the limit is in distribution. It's in distribution because in this situation, the stochastic effect dominates. It's in distribution, but the problem is that we don't have a good distribution because the only reference measure we have is infinite. Is in distribution in the unit tangent bundle with a measure mu for all probability measure which is absolutely continuous with respect to the Liouville measure. This is exactly the same kind of situation as for the central limit theorem here. That is, we don't only have the convergence in distribution for the Liouville measure, but for any probability measure which is absolutely continuous with respect to the reference measure. Because it's very close to the, it's more like an equivalent of the Birkhoff theorem. There is actually an abstract result. You have a Hopf ergodic theorem, which tells you that when you have a conservative and ergodic dynamical system with an infinite measure, finite or infinite measures, the Birkhoff sums or Birkhoff integral of a given function, of any two functions, will behave the same as long as they are integrable. So that means if I manage to prove this theorem for one function, which may be as smooth as you want, I get it automatically for every integrable function. What?
Why is the bar around the normal?
Well, it's an integral of positive. Well, imagine that f is positive and it's an integral. Actually, it don't have much to do with the normal variable, but it's a special case of a different family of random variables. If d equal 2, you will have to change the square root of t to a log t, and the absolute value of a random variable of a Gaussian random variable here will change to an exponential random variable. So this is to say the Gaussian random variable is not anything special here. And this is an equivalent of Birkhoff ergodic theorem for this kind of system. Now we have the same problem, that is, if f has zero integral, well, this converges to zero in distribution. So it does not tell me much about the asymptotic behavior of the Birkhoff sums. Well, just an aparté. This can actually be seen as a weaker form of a local central limit theorem. That is, at any time you can look at the point on which the geodesic flow is on this manifold, and you will get a central limit theorem. And if you look at the probability that the geodesic flow is in some region, fixed region of the manifold, you get a local central limit theorem. And this is mostly a weaker form of a local central limit theorem.
So you restrict to 1 and 2, c'est-à-dire to have the ergodicity of the geodesic flow?
Conservativity. Well, yeah, I think you always have ergodicity, actually. But, it's, so here is mostly the subject of my work from a PhD here. So what happens when you look at function with zero integral? We will have a condition of smoothness, like here. So we assume that d equal 1 to simplify. For all function f from the unit tangent bundle to R, which is holder and with compact support. For all probability measure on the unit tangent bundle, which is absolutely continuous, and the integral of f, I look at function with a zero integral, and the result I have is that the limit in large time of 1 over t at the power 1/4 of the Birkhoff integrals will be equal to the constant which depends on f times the square root of the absolute value of a Gaussian random variable times another Gaussian random variable where n prime are independent. And the constant which depends on f, it's again a semi-norm, and it will be 0 if and only if f is a coboundary. And this is, as I will try to explain you, the techniques behind the proof of this theorem. So, like I said, I want to get rid of the geometry. So I will go back to my first small drawing. The idea is to introduce just a section of the flow, of the geodesic flow. So, for instance, I can find section A, which will be transverse to the flow. Actually, it's a section in the unit tangent bundle, but to simplify, I draw it directly on the manifold. So if I have a section, this gives me, well, the geodesic flow will come here and will come back. So I have a time r of x. It's the time of return time in A. And I have a transformation which to a point here gives me another point here. And I have a transformation t from E onto itself. And if you put a good measure on A, then it's a measure preserving transformation. And then you can see the geodesic flow on the manifold just as a suspension flow over the dynamical system AT. T tilde, I said. So it's a suspension flow over A, T tilde, and some measure mu tilde. With the height function R. And then I can use a work of Rufus-Bowen, which tells me that in this context, you can find some very good section of the geodesic flow. That is, you can find a section A, which is made of finitely many boxes. B1 to Bn. These boxes, well, I call them boxes because they have a box structure which is given by the strong stable manifold and the weak unstable manifold. And the application, the induced application is isomorphic to a two-sided Markov shift. That means that if I take one box here, so I say that B1, I will have a piece of weak unstable manifold and a piece of a strong stable manifold. And if I let it evolve under the flow and stop it when it reaches again the section, I will stretch under this direction, contract in this direction. And when it will stop, it will be along the unstable direction. It will exactly cover another boxes, or two other boxes, or three other boxes. So this is a Markov property, and we have a few more interesting properties. For instance, the return time R will be older. And since we have chosen to take strong stable leaves, the return time will be constant on the strong stable leaves, on the pieces of strong stable leaves. Well, if I have such a section on the geodesic flow on M, I can lift this section to get a section of for the geodesic flow on N. So this section will have also an infinite measures.
So this is not transversal to the geodesic flow. You have a piece of geodesic flow here. You're taking the weak and stable.
No, it will be weak and stable, but still transverse to the geodesic flow.
Ah, still trans. Okay.
Weak and stable, you have dimension 2, and the geodesic flow is only one direction.
Yes,
and this is transverse. I mean, it's in the two-dimensional manifold, but still transverse to the dimension to the direction of the geodesic flow.
Weak and stable is dimension 2. Strong
Yeah.
and stable is dimension 1. Strong stable
Yeah.
is dimension 1. Weak and stable is dimension 2.
Yeah,
So
but
you have a section in dimension
yeah.
which is a dimension of the bundle.
Mm.
Which is a dimension of the quantum bundle.
Yeah. It will be a one-dimensional piece which is embedded in the weak and stable manifold. Actually, it will be a line. It will be a sum.
It's not a local piece. Ah, okay, it's a line.
So the section is still two-dimensional. Well, and if I lift this section, I made it in blue. So for instance, I have a section here, a section here, section here, and the transformation, I start from a point here, x, I need another coordinate. So a point in my manifold, I can characterize it by 3 coordinates. I have the starting point and the section, x, the time I need to evolve into the flow until I get to my point, t, and well, since I have countably many pieces of my section, I need also a point p. So x is in A, t is in 0 R of x, and p is in zd. And the transformation, I let it evolve, I let t grow until it reaches R of x, and when it reaches R of x, I apply the transformation t to x. I add f of x to p, which means that x R of x p is equivalent to t tilde of x, 0, and p plus some jump function, f, which takes its value in zd. So the function f tells me when I start from the point x, how much, what is the coordinate of the next section I hit. So this is a suspension flow. X is a two-sided. Well, X can be we can find X if we have the piece of stable manifold and a piece of unstable manifold. So you can think that there are 4 coordinates: a piece of stable manifold, a piece of unstable manifold, a time, and a coordinate in ZD. And we'll have to make some reduction so as to get rid of as many of these coordinates as possible. The first thing is that instead of integrating f until 0 and t, what I will do is that when I reach one section, I will add some value of which will be yf of x and p is integral into 0 and r of x of f gs x 0 p ds. So instead of, I have a new system. Instead of integrating f as I go along the geodesic flow, I add this function each time across the section. It makes not much difference because the difference between the two processes is bounded. The second thing is that I will get rid of the stable direction, because I already said that the function R is depends only on the stable manifold, on the unstable manifold. It's constant on the stable leaves. The function f, you can assume that it is constant on each box, and then you have the function y of f, which depends on the stable direction and the unstable direction manifold. But if 2 points are in the same piece of a stable manifold, then they will get close exponentially fast. And since f is assumed to be Holder, that means that the difference between the Birkhoff sums in the 2 points will be bounded. So actually, 2 points in the same piece of a stable manifold, we have the Birkhoff sums of 2 points will have the same asymptotic behavior. So you can forget about the stable direction. More precisely, you would have to add a bounded and smooth coboundary to y of f to get a new function which will be constant on the stable leaves. But in short, the idea is that you can forget about the past, just worry about the future. It's good enough. And so my new process, since I have forgotten about the past, I get a one-sided Markov shift. So you have ATL. It's a one-sided Markov shift over the same alphabet. That is the second reduction you can do. So now you have two coordinates, that is a point position on the unstable leaf and an integer p. Well, I have a very large section, so I will specify one subsection, A0. And now I will look at the system not as a suspension flow over my large section of many, many pieces, but as a suspension flow over A0. So my flow, I will let it evolve. It may cross some number of sections and then come back. It may take a lot of time to come back, but it will come back since the geodesic flow is conservative. And now it's a way to forget about the position P. You have, when you look at this, you only have a new induced system on E0 and the suspension flow over this new system. What kind of new notation? Yeah. You get a new sided. And next, I induce. So it's an induced map on A0. And then the whole geodesic flow, you can see it more or less as the suspension flow. Phi of x, it's the first rotation time in A0. So it's a suspension flow. So you have a measure preserving map and a suspension flow over this measure preserving map, and it tells me everything I want to know about the geodesic flow on this surface, on this manifold. So one last thing to see before I start the last part of my talk is that the induced map. So it may seem that it is very ugly because I wait a lot before I go back to A0. I apply a lot of the map T tilde here. But it will also be actually a Markov map. Well, it will be Markov, but on an infinite alphabet. This is what this is a Gibbs Markov map. The idea is that instead of having a shift on an alphabet where the alphabet is just the boxes in the section, you have a shift on the excursions. That is, you look at all the boxes you go through before you go back to A0, and this gives you an excursion. There are only countably many excursions, and the induced map is essentially one-sided shift on this excursion. So it's a Gibbs Markov map, and Gibbs Markov maps are actually very convenient. They are very good spectral property, and we know very well their properties, including the question of decorrelation of decay of correlations. What? No, T1. So, how do we prove the kind of central limit theorem I claimed? So I will put last notation, one of the two last notation. Xf is the integral between 0 and phi of x of f.
So what you get is a one-sided Markov shift of this infinite.
Yeah. I put here. That is the total change of the Birkhoff integral in one excursion from 0. I assume that it only depends on the future. And I will take C of t is the local time in A0, that is the cardinal of that's the local time. I mean, I count the number of times I go through the section in A0. No, the question is, I wanted to investigate this Birkhoff sum. But this Birkhoff sum, it's 1 over t at the power 1/4 times, well, I went through A0 exactly psi t times, plus 1. If I start from A0. K equals 0, I took psi t minus 1 of xf composed to t k plus a reminder. That is, I just separate this integral in the integral in each excursion. This reminder, you can control it. It's a bit annoying, but nothing very difficult. The second thing is I will multiply by the square root of the local time here. So this sum is approximately equal to this one. I just made this quantity appear. But this, the local time in the square root of t, we can see by this theorem that is approximately a constant time in distribution. It's a constant times the absolute value of a Gaussian. But we take the square root, so it's the square root of the absolute value of a Gaussian. This, on the other hand, you have xf will have very good property. It will be an LP for all finite p. It will be smooth, well, Holder, and it will have 0 integral. So you are taking the sum of sequence of of the iterates of the Birkhoff sum. You are studying the Birkhoff sum of the function, which is smooth and has 0 integrals. So by version of the central limit theorem, a bit like this one, this is approximately a Gaussian. a constant will depend on f times a Gaussian. So this explains, at least, why we should expect this kind of asymptotic of a limit theorem. The problem here is I made something absolutely horrible. I have a sequence here of random variables, which I take at a random time. And even if the sequence of random variables has some distributional limit, if I take them at random time, I have absolutely no reason to get the same limit. That is the first problem. The second problem is that here, even if on this part it works, I have a product of random variables. Nothing tells me that this is a product of independent random variables. And I claim that it was independent here in the theorem. So the question here is, how do we make it work? Xi, So the idea behind it's a method which was introduced by two Hungarian mathematicians. Xi is a generalized inverse of the sequence of the Birkhoff sum of the first return time, which is to mean if I take tau n the nth return time in the origin is this thing, and then you have the local time in tau n is exactly n, plus or minus 1. So instead of, so the local time here is the generalized inverse of the nth return time. On the other hand, we are working with another sequence, Sn, which is sum of k 0 to n minus 1 of xf evaluated in tk. These two sequences are not independent. And this is a problem here. If they were independent, this argument will allow us to conclude immediately. But they are not independent. And the idea, it's a theorem. I won't state the exact expression of the theorem because it involves some notion of probabilistic coupling which are a bit heavy. For random works, it was due to so random works. So for random works, these two sequences are the sum of identically distributed independent random variables. So it's the method is Xi and Foldes. And this is, well, 2012, I think, for the Gibbs observables on Gibbs Markov dynamical system. So their method relies heavily on the independence, so it requires some work to obtain it in the Gibbs Markov case. So the idea is that tau n and Sn are asymptotically independent. They are not independent, but for large n, it will look a lot like independent random variables. The idea is that to get the precise statement, you take copies of tau n and Sn which are independent, so you get a new stochastic process, and you can couple this, you can get a coupling of this process and the new process which is very close to the diagonal. So this process is very close to an independent process in some sense. And the reason why they are independent, it's a bit like magic. It just relies on the distributional properties of phi and x. The idea is that phi is the return time in A0. It has very heavy tails. That is the probability that phi is larger than t. It's of the order of a constant over square root of t. So there are very heavy tails. And on the other hand, Sn will be in L2. It will be in Lp for p larger than 2 even. So it will be very integrable. Which means that if I look at the Birkhoff sums here, I have a Birkhoff sum of a lot of random variables which are very integrable. So most of the sum will be due to a lot of small steps. There is not at some point one very large step which will dominate everything. It will be a sum of very small steps. On the other hand, when I look at the sum of such random variables, which are very heavy-tailed, the largest part of the sum will be due to a small set of exceptional events where the sums will be very large. Which means that if I take on one part the point where this is very large, and I can modify it how I want, and it won't change. I mean, if I take on one hand the step where this is large, and on the other hand most of the steps here, I get two processes, one which will be very close to this process, and one which will be very close to this process. And they will be disjoint, independent in some sense. That is the idea behind. So it works very generally. I mean, there is nothing special about the fact that this is the return time to random walk. We only need that it has a heavy tail, nothing more. And to work with Gibbs-Markov case, in the Gibbs-Markov case, well, it's a bit more complicated because the regularity of the observables is important. So we will need estimates on the regularity of the first order time, regularity of XF. Since it is not independent, there will be a lot of work to do to make the same idea to get through. But the idea is basically the same. And at the end, so we can prove that the local time psi and the sequence here are almost independent. And from there, we get this theorem. Okay, I think I have spent 1 hour, so I will stop here.
Question?
So what are the adaptations for case d is equal to 2?
If d equal to 2, I said here, but we can replace square root of t by log t, and the random variable here by an exponential random variable. So in dimension 2 here, I will get 1 over the square root of logarithm here, and we'll get here the square root of an exponential random variable.
But still a normal.
The second Gaussian here is always there.